today is somebody I met when I was in St. Louis at the AAS conference. And we actually, I think, just happened to be at the same table, and we were just starting up a conversation. And then he mentioned about how he was working on a project to put a neutrino detector in space. And me, I initially go to Kamiokande, Ice Cube, big old things, and I'm like, how is that going to work in space? And then he said, NASA's even interested, gave me some money, and I was like, how's that really going to work? So I said, you got to come and give a talk. So Nick is here. Nick's on the floor. Now you'll
Thank you very much. I'll try to just talk from here because there's a microphone, although I'm not going to be quiet. Today I'm going to be talking about the development of a neutrino detector for a space flight that's being done in cooperation with Marshall Space Flight Center, JPL, and University of South Dakota, as well as other faculty and students at my home state of Wichita State University. I'm going to give you some background information. I won't dwell too long on it. But the background is, and first, a disclaimer is that I'm not an astronomer and not even a space scientist. I'm just a simple particle physicist. I've been doing experiments at CERN in Geneva, Switzerland, and Fermilab in Chicago, and I've been the spokesperson of 2 small experiments in each of these labs. So I have a long career of doing particle physics. However, recently, particle physics is becoming an important role in astronomy and spacecrafts. And I'm going to give you one example. It's not necessarily the most recent example, but I like this one because in 1992, NASA launched an experiment called the EGRET spacecraft. It was a stack of spark chambers. And of course, my own PhD thesis advisor, who got the Nobel Prize in 1992, was furious to find out that NASA is launching a spark chamber into space, since no one's used spark chambers since the early 1970s. But NASA made a good decision there because you could take a spark chamber, you could punt kick it across a soccer field, you could pull it out of the mud, it's still going to work. It's a very reliable detector. But what NASA was able to do for the very first time was get above the atmosphere and open up our eyes to a brand new form of astronomy called high-energy gamma-ray astronomy. And this is an all-sky map from that EGRET telescope after about 5 or 6 years of data taking. And so we opened up a whole new eye by putting a very simple instrument someplace only NASA could put it, someplace unique, high above the atmosphere. And, NASA's done this with other things like Hubble. I mean, no one would call Hubble a great telescope. They'd call it the best observatory in the world. But it's a small mirror, right? So there's examples. So could we do a neutrino detector in space? And what advantages would it have for doing physics, astronomy? Could it open up a new eye? Well, I'm not going to dwell too long, but a lot of people, I'm assuming, are not neutrino physicists like myself. And I'm not going to cover the whole field of neutrino physics, but I have written a few books for the public. One of those books is called The Elusive Neutrino, which is a 12-chapter book about the history of the neutrino and some of its outstanding mysteries. And so if you have interest in time, it makes a great Christmas gift. You can buy my
How
book,
much
The
is the
Elusive
book?
Neutrino. It's $40 from W.H. Freeman. So let me give you a history of the neutrino. Early days, when Curie and Becquerel first discovered radioactivity, they noticed 3 types of particles: a neutral gamma ray, positive alpha, and a negative beta. And they were able to understand the alpha decay. When you measured the energy of all the alpha particles, it had all the missing mass energy. However, when you looked at a beta decay, the beta decay particle with the electron had this really weird spectrum of energy of the outgoing beta. The maximum energy that was being released in the reaction should have been here, but you were only seeing some fraction of the energy being released. And that was a mystery until Pauli proposed that this particle, the neutrino, which Fermi coined in Italian meaning little neutral one, was actually emitted along with every electron, and sometimes the electron got more energy, sometimes it got less, and when the electron got less, the neutrino got more. And so the neutrino was actually born. And yes, that was a theoretical idea, but eventually the neutrino was discovered and directly observed using a nuclear reactor. It was actually done with antineutrinos. Antineutrinos on protons were able to produce a neutron, and then the neutron itself, and the fast electron, then the neutron itself would eventually be captured in a gadolinium dopant. And they were able to see on the surface of the Earth, without any shielding, without going deep underground, 2 detectors, signals. One they called the positron camera, one they called the neutron camera, and they were able to see a time delay, but because it fell within the window of after their first observation, they were able to say, this was the neutrino interacting in the detector. So it was a very good way to clean up the apparatus and the signals, because obviously nuclear reactors can produce a lot of garbage. Yeah. So solar neutrinos are a little bit harder to detect because they're actually neutrinos, not antineutrinos, because they're coming from the fusion process in the sun. Everything else that we deal with here on Earth, whether it's a nuclear reactor, radioactive decay, it's almost always emitting antineutrinos, and neutrinos are actually being born mostly in the core of the sun. And the solar neutrinos were very hard to detect due to their low rate. But from 1970 to 1994, a man by the name of Ray Davis in the Homestake Mines in South Dakota was able to observe solar neutrinos directly. He did it through an unusual process. But just to point out, here's the reaction of protons fusing to make eventually helium. And then there's several chains in here that emit neutrinos from the process. And by the way, there has been other places we've seen neutrinos other than the sun. We saw neutrinos from the object called 1987A supernova. We saw 12 neutrinos in one experiment and 8 neutrinos in another back in 1987, all within about less than a fraction of 2 seconds of each other, all of which were highly above background. And if you don't count the high energetic neutrinos currently being observed by the IceCube experiment at the South Pole, then these are the only two sources of neutrinos we've seen. The reason I say that is because IceCube is seeing very energetic neutrinos, 70 GeV and up, but they don't know where they're coming from. They haven't identified any of those specific neutrinos with a specific source in the night sky because they don't have enough statistics to yet, but eventually I'm sure they will once they do get enough. So the missing solar neutrino mystery and the discovery is coupled to the discovery of neutrino oscillations. And the experiment of Ray Davis to observe solar neutrinos was using neutrinos from the sun being captured on chlorine-37, and then it creates argon-37 plus a positron. And no, Ray Davis did not try to find that positron. What he did was he tried to chemically sieve all of his chlorine and take it through a scrubber that would then be able to accumulate the argon-37, which then he could identify by radioactive decay and count how much argon-37 was being created, which is a very slow task because he was only expecting a handful of neutrinos per day from the sun, even though his underground tank, and here's a picture of his underground tank with him on top of it. Who's in the background there? So, it was a very large experiment with a large tank, and there was a mystery, and the mystery was that there weren't enough solar neutrinos. The neutrinos were missing by a factor of 3 or 4, almost. And eventually, we were able to answer that question because eventually he was able to say that it's neutrinos oscillating as they fly. And this was confirmed by the Super K, or Kamiokande experiment in Japan, using not neutrinos from the sun, but using neutrinos generated by cosmic rays in the upper atmosphere, and they were able to see a difference between downward-going neutrinos and upward-going neutrinos as the cosmic rays hit the atmosphere, either from above or from below. And this was really the key to both Ray Davis and Kamiokande experiment getting the Nobel Prize for this neutrino experiment result. Now, in the sun, neutrinos are being born as electron-type neutrinos. There are 2 other types of neutrinos called a muon-type neutrino and a tau-type neutrino. And as those neutrinos fly towards Earth, they oscillate into even though they're born as electron neutrinos, they oscillate into muon neutrinos and tau neutrinos. By the time they reach us here at Earth, which is very far distance away, they actually have transmuted themselves into a certain fraction being electron neutrinos, a certain fraction being muon neutrinos, and a very small but still present fraction of neutrinos being tau neutrinos. And this is where we are on Earth. Now, the beauty of the neutrinos is a little different than the sun. Everyone sees the sun. It's a nice hot ball. If you've ever been to a totality solar eclipse, You're looking at the sun, it's bright, it's bright, it's bright. All of a sudden the moon blocks it all out, and boy, it's dark. The sun is very bright. But that light that you're seeing was made, the energy from that light was actually created 80,000 years ago in the core of the sun. It takes that long for the energy from fusion to boil to the surface, which then makes the light. Neutrinos don't interact with anything, practically. Even though they have mass, but no charge, they only interact weakly. So they're able to actually go right through all that matter through the core of the sun and come directly to Earth in 8 minutes, directly from the core. Whereas if you're looking at light, you're looking at the energy created in fusion reactions 80,000 years ago. So we can actually learn a lot if we could study the sun in neutrinos a little bit better. And people have been detecting neutrinos from the sun now for about 20 years, obviously, from the Ray Davis experiment. But it's not a huge number that we have. Even though we have these huge, big experiments deep underground, we still only have a couple hundred worldwide events. So I asked the question, can we operate a neutrino detector in space? What new science can be done? Here's a table, for example. Here we are at Earth. And if we take the flux of neutrinos at Earth to be 1, if we get up to 7 solar radii, then the neutrino flux would be 1,000 times larger, just because the 1 over r squared. If we go to 3 solar radii, we're at 10,000 times the flux of solar neutrinos here at Earth. So imagine you have this experiment here on Earth, which is a ton, which is 1,000 kilograms. So we have a 1,000 kilogram detector, and we wanted to get the same rate. If we go to 7 solar radii, that's about the distance the Parker Solar Probe Plus is. This Parker Solar Probe is now. And that would mean you could do the same exact science with a kilogram size detector. So that's pretty impressive, right? Now, if you had a 250 kilogram detector, you'd be able to do 250 times better than the Canland experiment, which is a kiloton of solar neutrino detection here on Earth. You would also then, if you're able to get the 3 solar radii, which some NASA people think is possible, then we would be able to get then to an even larger fraction of neutrinos, and we could measure in a few days what we've collected in all of our experience so far. So on Earth, a few hundred solar neutrinos have been detected. When we get to the surface of the sun, we get to 45,000 times better, and more intense. It turns out dark matter is also currently being limited by our abilities to detect dark matter above a solar neutrino background, because it turns out solar neutrinos emulate what a dark matter signal could look like. And in the converse of this, if you go away from the sun, the solar neutrino background drops. In fact, the Voyager 1 probe in the year 2015 is 0.0006 times the neutrino flux here at Earth. So you can take that solar neutrino background floor, which a lot of experiments are closely approaching, and you could smush it down 3 or 4 orders of magnitude. Now, without waiting for a nearby supernova, it's also going to turn out to be possible that I could use the gravitational focus of the sun to actually concentrate neutrinos from a distant source, and I could concentrate the neutrinos in a very large concentration. Now, you can't use the sun to image the sun. So you can't use the gravitational lens of the sun to image the sun. So you ask the question, what's the second brightest source of neutrinos in the night sky? And it turns out the second brightest source of neutrinos in the night sky is our galactic core. And our galactic core, the really core part of it, is about 2 moon diameters across. And that's a pretty small source by comparison. And so these are the 3 topics I want to expand upon. And I'll tell you more about them, but that was just my introductory slide. So studying solar neutrinos from the solar core is a little bit interesting and mysterious. We actually have neutrinos from a high energy physics process that we expect here out to 10 MeV, and the boron 8 out to 10 MeV. And we expect PP fusion processes to end somewhere around 0.405 MeV. And we expect to be able to see beryllium-7 and the PEP signal. Those are the dark lines. Well, this beryllium-7 should have been a dark line also. But there's other fusion processes in the core of the sun that the standard solar model says should be occurring right now. Those are a low concentration of oxygen fusing, fluorine fusing, and nitrogen fusing. Now, they're only in dashed lines here because they haven't been seen yet. Even though we see the boron 8, we see the energy physics line, we see the proton-proton line, we see these PEP lines and this beryllium-7 line, which mistakenly should have been solid. We don't see these other fusion processes, which should be a higher rate than, of course, the boron 8. So there's something wrong with there's still something wrong with the standard solar model. It could just be that our sun isn't actually as old as we think it is. It just might not be, I mean, these lines might exist, but they might be an order of magnitude lower if the age of our sun is just half a billion years less. So, yeah, that's, our sun is estimated to be 4.5 billion years old. If it was just 4 billion years old, this would easily explain it. But by going closer to the sun, you could be able to actually get a higher intensity, and you can see these processes. The other things that are confusing about the standard solar model that we would like to address is where are these fusion processes occurring? And of course, everyone really says, oh, it's in the core of the sun. Well, everyone knows Gauss's law, and everyone probably knows that if you were in a cavity inside the center of the Earth, you would be weightless, right? Because all the forces of gravity from all that mass cancels. So the fusion of our sun doesn't actually occur in the center of the sun. It occurs slightly offset by about 0.1 solar radii, and some of the fusion processes of these different versions are all the way out to 0.2. And some of the mysterious ones that are missing, like nitrogen-13 here in this blue, or the oxygen is somewhere between these two cycles. And it's in certain layers. So at Earth, so a spacecraft in orbit could change distance as go off axis of the ecliptic. We would be able to then, if we go off axis of the ecliptic, the plane that all the planets are flying on, and we go to higher latitudes around the sun, and we collect enough data, we could merge some assumptions and assertions with the data, and we could actually then be able to reconstruct what a 3D image of the fusion toroid would look like. And so that's one thing we can do that can't be done by measuring neutrinos on the Earth. You can't right now determine what the toroid of the fusion process looks like. And that would be really great to do that. At Earth, the neutrino oscillations are coherent. What that means is by the time those neutrinos get to Earth, they actually, the number that's electron neutrinos, the number that's muon neutrino, and the fraction that's tau neutrino is fixed. And that doesn't change. You can fly all the way into the sun, and that doesn't change until you get to about 35 solar radii, where all of a sudden 10 MeV neutrinos are no longer coherent closer than 35 solar radii. You start to see that the concentration of electron to muon to tau starts to change. And so we can actually map out what that line looks like, and that line is actually dependent upon various theoretical curves. And there's some data trying to get to it, but every experiment's only able to produce one dot on this, and they're very broad error bars, so they're not actually measuring it. But we think they're measuring from these 4 experiments something to do with it. But you can see that as the neutrino energy changes, 1 MeV, 5 MeV, 10 MeV, then the coherency length and the oscillation length changes. And so then we're talking about 35 solar radii for 10 MeV, about 8 solar radii for 5 MeV. And unfortunately, 1 MeV neutrinos is right there at the surface of the sun. But I'm not saying we're going to measure all the way down to there. But it is interesting that it goes down all the way to almost the surface of the sun. And the first thing that I was surprised about when I looked this up, because I was trying to figure out what we could do with the data we could collect in this futuristic project. And I was surprised to find that this decoherence length from the center of the sun is actually much further out than I originally thought. I originally thought when I was going to do this, everything would be inside the sun. But no, 35 solar radii, we've already sent in the 1970s 2 probes to within 30 solar radii. And now we've sent the 3rd probe to within 8 solar radii. Well, it's eventually going to get to 8. I think they're too scared to put it in closer than 10 right now because they don't get lots of data. So eventually, as the spacecraft gets older, they'll push it in closer and closer with every flyby by means.
What's the time frame for the oscillation of the neutrinos?
Oh, the time frame, it takes 8 minutes to fly here. The time frame is, less than a fraction of a second. It just keeps oscillating back and forth.
And would your detector have sufficient time resolution to see all those?
We'll have space resolution. All we need to do is, at 1 MeV, we just need 34 kilometers spatial resolution from the core of the sun. At 10 MeV, we just have to have 340 kilometers spatial resolution. The claim of NASA is that, I'm not a scientist that can do that myself. The claim is they can do that. Accuracy. It's using measurements of lots of these guide stars. I guess people here know a lot more about that than I do. But it's astrometry.
Astrometry.
Yeah, the claim is by NASA they can know the distance down to a few kilometers.
That's true.
I thought the Davis experiment found too few neutrinos because they were oscillating. Are you saying if the Earth was just a few kilometers closer to the sun, which it does, then
No, I'm
the
saying
rate
that.
would be different?
No, that's not correct.
No, it's actually coherent. By the time you go more than 35 solar radii away from the sun, the mixture is fixed and coherent. Are these neutrinos constantly changing? Yes, they are. But the coherency rate, which fraction is electron neutrinos, what fraction is muon neutrinos, and what fraction is tau neutrinos is set to a constant once you're more than 35 solar radii away from the sun.
The solar neutrino problem that Ray had was that we only knew about the electron and the muon neutrinos. We didn't know about the tau at the time. So he was finding it only a third of what he thought we should do.
Okay.
So is it like half the distance of Mercury? I mean, so Mercury is like 30 plus million miles, and the radius is...
The rate doesn't change.
You have to go back and look.
Mercury is there. Yeah, Mercury is, the neutrino flux would be 6.7 above that of Earth. And of course, as you get closer, all these other numbers are just distances in kilometers. Okay. So, onwards. Dark matter. The discovery of dark matter, which is one of the highest priorities of NASA Astrophysics Division, as well as a high priority NSF, is limited here on Earth because of a solar neutrino background. So how do we know that dark matter exists? How do we search for dark matter, backgrounds to dark matter? Well, we know dark matter exists because we've looked at rotation curves of galaxies. Given the amount of light that's out there, we're able to say that this red curve should be the calculated rotation curve. And when we look at the spectrum Doppler shifts, we see this white curve. And so that can only be accounted for by the additional matter that's not glowing. Okay, that's the first evidence. Dark matter today is assumed to occupy, in our best theories, 27%. Atoms about 5%, and dark energy about 68%, but that wasn't always the case. If you go back to a few minutes after the Big Bang, dark matter was occupying 63%, then photons 15%, and neutrinos 10%. So today, visible baryonic matter is less than 5%, and dark matter is 25%. So science would like to directly detect. Now, this is an example of all the experiments out there currently searching for dark matter. And this yellow line here is called the neutrino floor. This is coming from solar neutrinos. And if you can't detect where the neutrino direction is coming from, which you can't, then these experiments, once you push them down to this far, you can't actually, you reach the solar neutrino background limit, and you can't go any further. So yes, out here we could actually go still down almost an order of magnitude in searching for dark matter. Here we're getting very close to it. But this bump here is actually all due to the sun. It's solar neutrinos. That's because 8 MeV neutrinos from the sun emulate and look like 10 GeV over c squared particles in a dark matter experiment. So, well, if we don't detect dark matter pretty soon, we're never going to discover it, right? Well, definitely not on the Earth. But if you're able to take an experiment and go very far away from the sun, then you would actually be able to push these limits down. Like I said, Voyager probe was 6 orders of magnitude out. So you would actually be able to take this big, huge thing and lock it down to here. Now, I don't have any tricks to get rid of this background here, because that's from the galactic core and from deep space. But we could definitely take the solar neutrino background, and we could lock it down to pretty low. And that would give you, and that's interesting because this experiment here is getting to a candidate that has a 6 GeV over squared dark matter signal. But by the time they reach that, it's going to be solar neutrino limited.
What's your abbreviation, DSNB neutrinos?
It's
See, DSNB neutrinos.
Deep space neutrino background.
Atmospheric and DSNB.
Deep space.
space.
No,
Neutrino
deep
background.
space.
It involves
Deep space
things
neutrino
like
background.
quasar neutrinos that are just coming from all different directions.
Okay.
It involves all sorts of neutrinos that may have been created by supernovas that don't.
Right.
Well, we don't have any timing right now, but they're just coming from every direction.
Okay, thank you.
So we've been actually studying with a graduate student of mine and South Dakota State University and Marshall Space Flight Center the idea of designing a detector that would actually be sensitive to dark matter and to put it onto a small CubeSat and send it off into deep space. And we had a problem in that this would require, if you go really far away from the sun, you can't use solar panels anymore because there's not enough sunlight. And so JPL actually has found a solution to that. They claim that they could put a small spacecraft in a bubble of mylar, and one end of it be aluminum coated. So if they took a 12-meter diameter bubble of mylar and they put the small CubeSat at the focus of it, they could then have a concentrator that's 12 meters across to concentrate the light onto the solar panels of a spacecraft. And the bubble would solve several problems. And the bubble would give you a bigger radio dish to talk to Earth. The bubble would give you a light collecting power to collect more sunlight. And the bubble would actually be filled with a small amount of carbon dioxide gas. And that would actually be enough gas to heat up the environment of the spacecraft so you don't have to take a lot of thermal management with you because of the inside the bubble. So that's another project that is part of this that I'm not going to talk about at all.
When you say this thing's a CubeSat, do you mean 10 centimeters by 10 centimeters by 10
This is a
centimeters? or something?
24U CubeSat.
Oh, okay.
Which is
Thank
20
you.
by 20 by 60.
Okay, a little bit bigger, but okay,
Yeah.
still pretty
But it's
small.
still pretty small, yes.
Right, thank you.
Who has developed this solar?
It's JPL.
JPL.
JPL has a project. You can look it up also on the NIAC website.
What's it called?
I forget what they called it, but if you go to the NIAC NASA website, you'll find my project is one of the NASA Innovation Advanced Spatial projects. And then I was talking with them during my NIAC Phase 1, because now I'm on a NIAC Phase 2 with $500,000 a year for what I'm about to talk to you about. And but they had the idea of how to solve my problem, and they got a NIAC Phase 1.
And how far out did you get?
They think they could go out to about 200 astronomical units and still have enough sunlight.
Wow.
With a 15-meter diameter.
That's being on
bubble.
Pluto.
Yeah. Oh, yeah.
That's a good reference.
Pluto's at 40 astronomical units.
How much does this stuff weigh?
That's way quite.
Oh, this CubeSat weighs very little. It's being designed to be less than 12 kilograms.
I mean, the extra thing for the...
It's just a mylar bubble and some thrusters and gas to keep it inflated even if it has leaks. And it's not that much. Okay, the last project I want to talk to you about is gravitational lensing. Gravitational lensing is a really neat idea, and it's actually a high priority of NASA because NASA wants to be able to image an exoplanet. And they want to have enough resolution from an image of an exoplanet such that they could actually identify a 10-kilometer by 10-kilometer structure on the surface of an exoplanet. In other words, they're looking for continents, they're looking for oceans, they're looking for ice caps, they're looking for structure on one of these planets. And the Congress here in D.C. has actually passed a law, and the law that Congress passed last year was that by the year 2069, the 100th anniversary of NASA landing a man on the moon, NASA should launch a spacecraft to the nearest star, or a spacecraft that can image a nearest star with a resolution of 10 kilometers by 10 kilometers. And so NASA thinks that gravitational lensing, and gravitational lensing just comes from Einstein. Parallel light comes near the sun and it gets concentrated.
Congress have any idea how?
No, they just
Of course not.
They'll all be out of
It was
office.
passed to honor the
Or
50th
dead.
anniversary of landing on the moon. And it gave NASA some challenges, but it gave them some extra money, because money actually came with it. And so there are people like JPL has a whole division now dedicated to gravitational lensing imaging to try to go after that money. But if you look at some accidental alignments, this is a star, and the light is actually being accidentally concentrated because of an object that's off axis.
Just by a little.
Just by a little. It's not that little, because I'm about to show you which star this is, produces this ring. Now you can tell it's off axis because there's a gap up here.
All right.
The gap also tells you that the object you're imaging is up here. That small amount of light that you're seeing directly is resulting in this huge amount of blue light here due to gravitational lensing. It's 10 to the 12th times more light in the gravitational ring than it is directly observed.
Damn.
That's impressive.
What's the mass of that star?
I have no idea. But this is an example of the light enhancing power.
It's amazing.
I don't even think it's a star. I think it's a blurb of something like a...
No, the lens star.
Oh, the lens star. Oh. No one's ever asked me that question. This is called the Horseshoe Ring, not to be confused with the Horseshoe Nebula, and you can look it up. But it just shows my example of concentration of light, that it's this little blue object that's producing all that light. That's because I need lots of light collecting power for neutrinos, since it's a weak signal. Now, gravitational lensing of neutrinos, because neutrinos have mass, you don't have to go out to the gravitational lens distance of light. Gravitational lens distance of light is not close to us. It's 550 astronomical units away. In all of the 44 years the Voyager probes have been flying, they've only managed to go out to 135 astronomical units. And you have to get for light out to 550 astronomical units, and then that's just for the red light. And then as you fly further, you go all the way out to 750 astronomical units for the blue light. And then you have these rings of light that you would then image and be able to reconstruct the image that your gravitational lensing is seeing. But the neutrinos have mass. Their gravitational lens point is much closer, and their gravitational lens point is somewhere like 20 astronomical units.
Wow.
That's only to the distance of Uranus. Now, I must admit, something just recently changed on December 3rd. A new article was published with an experiment that they've just taken the limit of the neutrino mass of being less than 1.1 electron volts, and it's now 0.8. So it's now more like 30 astronomical units. But it tells you another thing. Everyone has said that measuring the neutrino's mass is really hard, and we may never be able to measure the neutrino mass. Just find where out the neutrino gravitational focus is, and it tells you exactly what the neutrino mass is. Wow. It's actually a particle physics experiment. You find where the neutrino mass, you find where the gravitational focus is of neutrinos, you know exactly what the neutrino mass is.
That's elegant.
That's elegant. It's a second way to finally look at measuring the neutrino mass, because Germany is trying to build a new experiment for measuring the neutrino electron mass. And they had a major problem. They built a radioactive source in Russia that would actually be able to be used for it, and the source unfortunately exploded, and they contaminated a couple cities.
Yeah.
And then Russia, the company that's doing this for them in Germany, sent them a note saying, we can't produce this source for you, we cancel your contract. And so they're now stuck dead in the water.
But the different neutrino flavors have different masses, and one of them is significantly lighter than the other two.
Right. Okay. All fusion reactions are born as electron neutrinos, and their energy is too small to make muon neutrinos. So when they oscillate from electron neutrinos into muon neutrinos or into tau neutrinos, they don't have enough energy to create muons when they convert. So all of these fusion reactions, neutrinos from the sun or from distant stars, is a disappearance experiment. It can't be an appearance experiment. Because the neutrinos of muon type or tau type that you produce are below production threshold, and it means they won't interact because there's nothing for them to interact into. A muon neutrino would have to interact around matter, and that interaction around matter would have to have enough energy to make a muon, which isn't going to happen because they're born in the solar furnace.
What I meant is the focal distance depends on the mass.
Yes.
And the different neutrino flavors have different masses, so the focal points will be different.
Yeah, but you can't measure the other two. You can
Okay.
measure the electron one. It's impossible to measure the muon one or the, unless you happen to get a supernova that produces muon neutrinos. So I understood your point, but it's impossible because they're below threshold of production.
Just wondering, that sounds like a really difficult experiment to measure the gravitational focus distance.
It would be on a point source, but because the galactic core is not a point source, that makes it possible. Well, I'm getting to that. The gravitational lens of the sun is actually, even for neutrinos, is even better than for light. Because the sun is transparent to neutrinos.
Sure.
Low energy neutrinos go right through the sun as if they're not there. And so a distant object, not only does it have the light collecting power of 10 to the 12 of light, but it actually can go into the core of the sun, and it turns out the neutrino collecting power of the sun is 10 to the 15, not 10 to the 9 like light. That gives you another few orders of magnitude. And it's not like I need every order of magnitude, but I do. So a broad source can have off-axis imaging. I already showed you that with that star, with the blue ring that was not closed on one end. That was an off-axis imaging. So now, even though the core of the sun, the core of the galaxy is 2 moon diameters across, as viewed from the Earth, which I guess also means it's 2 sun diameters across because the solar system. But there's people who know more about that here than me. So it's a pretty broad thing, and that's what makes it possible to image this. So
You can image it, but you want to measure where the focus is.
I want to measure where the focus is, so as the spacecraft flies out, I want to be able to see a bump. But I also want to be able to image the core of the galaxy. And imagine you have a 1-pixel camera. How would you use a 1-pixel camera to make an image? You swing it, move it around, and then you get an image. Well, it turns out that even if I'm not able to take a spacecraft to Uranus or Neptune to measure the solar neutrino, because maybe I'm not going to, I haven't done all the detailed simulations of this yet, so we're just actually asking for money for this part of the experiment, because JPL and I just came up with this whole idea in the early part of the summer, and Mark heard about it first at the St. Louis AAS meeting. But imagine you need a bigger detector. You know, some people say, let's take an asteroid there. Well, that's hard to move an asteroid. Yeah. But you don't mind if I take a gas giant, do you? Yeah. I could do that.
It's already there.
Well, they're not there yet, but they will be. It turns out in the year, this is the galactic core right here. In the year 2034, we're actually going to have the planet Uranus right opposite the galactic core from the sun.
Damn.
And in the year 2066, where am I here? 2066, yeah. There, we're going to have Neptune right opposite the core of the sun. And now, if anyone's ever looked at the image of a gas giant on the dark side of the planet, what do you see? It's pretty black. Yeah. It's pretty dark. You don't see anything. You can see a little bit of light by looking off to the rings, or the limbs of Uranus. It's very dark. So now you've got neutrinos coming from the galactic core. They're being focused by our sun. They're coming out to some distance that's somewhere like 20 to 45 astronomical units away from the sun. And you now have a really large detector there called the planet atmosphere Uranus. Now, just like our Earth, or just like our sun, Uranus and Neptune is pretty transparent to neutrinos. So you can catch those neutrinos that are actually interacting as they exit the planet on the dark side, and you can image the light being generated from neutrinos interacting. And this is the project of a new thesis of a student of mine. We're doing it theoretically. And by the way, this has lots of actually good founding because there's an experiment NASA wants to fly on the International Space Station called the USNO project, which deals with using imaging of the atmosphere of the Earth in the night sky so they could look at cosmic rays and neutrinos interacting in the Earth's atmosphere because it gives them a big, huge target. And instead of looking at light coming down to the Earth like a lot of cosmic ray experiments do, you can just image the light that's also coming up from these neutrino interactions in the Earth in this USNO project. And so this is just a takeoff on the USNO project for using a different planet at the gravitational focus of the sun. So, now I've set you up. And the one question you should be asking is, okay, this is all exciting, but how on earth is he ever going to make neutrino detectors work in space? And that's the whole key to my NIAC Phase 1, which is a simulation, and my NIAC Phase 2 grant from NASA, which is a 2-year project that we're going to try to measure a detection technique we came up in our NIAC Phase 1. It's actually not that different than Ray Davis's. Neutrinos in Ray Davis acted on fluorine, made argon-37 and an electron, well, a positron actually, and he was actually able to count the argon-37. But it turns out we could use gallium interacting with a neutrino from the sun. There's 2 versions of gallium. They're going to produce a germanium, and in a fraction of the time, this germanium, yeah, there's like a third of them that are not nuclear excited, but in 2/3 of these events, the germanium is actually nuclear excited in either the M1 state or the M2 state, which means it decays emitting a gamma ray or an X-ray within a 5 microsecond or a 2.8 microsecond lifetime, and it emits a very well-known X-ray or gamma ray. So all we have to do, and we've simulated this, all we have to do is take gallium dopant, maybe it's 1%, maybe it's 4%, maybe it's 10%. I doubt if it's 10%, because gallium precipitates out due to vibrations if it's over 9% in concentration, and everyone knows that a launch is quite vibrating, right? Although my NASA colleagues say, don't worry about that, we'll just mix it when we get in orbit. Actually, they can do. But okay, I'm assuming we mix it here on Earth and it's going to be, we don't have to go up to 9%. So all I have to do is I have to look at, here's my gallium interacting with the solar neutrino. I'm going to look for an electron.
That's easy.
That's the easy part. But it's broad spectrum, and there's a lot of losses there because there's a tiny fraction that goes down to 0. So you don't get every single event. And then 2/3 of the event, or half of the events in this mode, are produced in a nuclear excited state. And in this time window of, let's say, 10 lifetimes after you produce this excited state germanium, you look for these very well-known lines of X-rays or gamma rays. And so you're looking for 86 keV X-rays 5 to 50, from 0 to 50 microseconds after. You're looking for 400 keV gamma rays, 2.8 to 10 times 2.8, and you're looking in this excited state of gallium-71. It actually has a 20 millisecond half-life and a well-known energy of 100. So that's the technique. And we've simulated that in GEON, and we've simulated that in our nuclear reactions, and we think we could do that. We have a strawman detector idea. The strawman detector idea is we have this liquid scintillator vessel. It's concentrated with 1 or maybe 5% gallium. It has phototubes on each end. It's surrounded by a Vito ray, and it's surrounded by some shielding. And we made some measurements to look at the different fiducial volumes, how fat the cylinder is, and how short it could be, to determine how much percentage-wise of the events we could collect just by fiducial volume. And we come up with an optimum somewhere up here, this purple line. And then we've been looking at how much shielding from the sun we need to be behind. The sun, of course, produces a lot of backgrounds that we have to take into account. These are called solar electromagnetic radiation and solar proton radiation. And if we had a 8 centimeter thick layer of tungsten as an electromagnetic shield, then we'd be able to reduce the sun's electromagnetic radiation by 5 orders of magnitude. So we've studied that. We've done lots of detailed neutrino interactions, as well as galactic gamma rays and galactic cosmic rays. This is my neutrino event. This is my cosmic ray event. This is my typical gamma ray event. And the detector here is the strawman detector of a liquid scintillator with phototubes, not phototubes, but they're photosensors, because they spin things nowadays, called microchannel plates. Surrounded by a veto ray, surrounded by some shielding. There's a electromagnetic shield, which is blue, and then there's a sunshade, which is red. Something is probably ceramic that's not going to stop the electromagnetic particles, but it would definitely stop most of the heat.
I'm sorry, what do you mean by strawman?
Well, when you throw together a concept, you take a strawman design, which is something you guess at as your starting place. Eventually, we've already started on our NIAC Phase 2 to refine this, because we've learned that this detector can't be very long. So now we have two solutions to that. One solution is to make the detector fatter and shorter, which will then keep the light collecting power for the gamma rays high, but that then forces the tungsten shield to become fatter, and that becomes heavier. So then we're talking about taking two of these and putting them in a row. That would then keep the electromagnetic shield mass low. So a strawman design is like when you first design an accelerator or first design some detector. You just draw something up, what you think is your best guess, but you haven't done the detailed simulations yet.
But you've done some simulations.
Yeah, you've done a lot. That's why our strawman design is starting to change. We've learned a lot, but that was still just a picture of our strawman design. And by the way, it's only changed because our NIAC phase 2 is actually just started in August 31st, and so this is new results.
How long does the phase 2 last?
2 weeks. And we're building a detector. I'm coming to that. Okay, so we have these Xenon simulations. We were actually able to take our strawman detector. We were able to take the number of neutrinos we thought we would get, that's 7 solar radii. We were to throw in their radiation from the sun, behind the heat shield and behind the electromagnetic shield, throw in the galactic gamma rays, which we got from the Fermi telescope, throw in the galactic cosmic rays, which we got from another NASA telescope, and then try to reconstruct everything out and see what it looks like. And the 3 different modes look like this. You can still see the characteristic half-life, and you can still, but some of these involve a good 20% of non-neutrino events in here. But you can still, even with this looking kind of ratty still, you can still see the lifetime of that secondary pulse of the gamma rays. And yes, we're having like 20% contamination in our strawman detector design, which was the best design I have to talk about right now, because I don't have the revised stuff ready to talk about yet. But you're still seeing the 3 characteristic lifetimes, and we took all the correct rates that we expected, the correct rates of galactic cosmic rays, correct rates of galactic gamma rays, the solar neutrino interaction rates, and all the inefficiencies that come with it. And this comes now down to the key point. What can we do? Well, we settled on talking about a 250 kilogram active detector. And we're talking about 7 solar radii away. Let's compare it with a new experiment which is just being built and has 1 year of data taken so far, the 300-ton Borexino experiment. And in the range of 0.4 to 0.8 MeV, they're seeing 15 neutrinos per day. We're estimating 150 per day. 0.8 to 1.5, they're seeing 3.5 per day. We're looking at 35. So we're essentially, with the 250 kilogram detector, 10 times better than them. And we could do things they can't do. We could go to the decoherent length of neutrinos from the sun. We could go off axis to get an image of the toroid of fusion around the sun. This all requires lots of things I have no idea how to do, because I'm a particle physicist. But NASA says they know how to do all this. They know how to know the location of that satellite if they had to within 3 or 4 kilometers with guide stars. I don't know if that's true, but they say they can do that. And they know how to get it into space and operate in space, so I'm not an engineer. But this is the key point. We think with a small detector, we could actually... Now, NASA has since then told me, as part of my NIAC Phase 2, they want me to do the following. they want me to come up with an estimate of what is the smallest satellite you could come up with. And can you show that it's, including the launch and 5 years of operation, that it's going to be less than $350 million? Because if it's less than $350 million, they'll make it a small class Explorer project, which is something that NASA does for the first time in space. And if you show it's less than $350 million, including the launch, you can get approved to do it fairly quickly. And to NASA, fairly quickly means 8 to 12 years, which is impressive fast, they tell me.
So
I'm a particle physicist. I know that accelerators take 20 years to design.
And build.
And build.
Who's going to do the cost estimate?
It's the Advanced Concept Office at Marshall Space Flight Center is doing the cost analysis.
Multiply by pi.
They came up pretty close to Solar Probe Plus. They were only off by a factor of 1.2. Okay, anyway.
20%.
So we're trying, as part of the NIAC Phase 2, to build the detector in the lab. We are constructing the strawman detector, because that's what we had. We'll probably end up checking. It's only going to be a quart-sized detector. And someday we hope to fly it in space as a CubeSat, just to prove they can operate in space, which is something we need, because a neutrino detector has never worked in space. We have technical readiness level 1. In other words, it's just a piece of paper back in an envelope. But we've actually, I think, gone. They actually have listed us now as technical readiness 3 because we've done simulations. And so this is a great scientific potential for a spacecraft, even if it doesn't do better than the neutrino detector on Earth in counting rate. It could go off axis of the ecliptic. It could go into the decoherence lane. It could, even if it was just the size of a detector that was equal to something here on Earth, it could still do unique things. And can we make that detector less than $350 million? And by the way, a Falcon launch is only $80 million. So that's good. Because in the old days, a Delta launch was $300 million, and you only had $50 million left. So this is of interest to heliophysics, to study the sun, astrophysics, to image the galactic core, particle physics, to look at neutrino transport, neutrino oscillations, direct measurements of neutrino mass, maybe even dark matter searches. So this is the project, and it is now in a NIAC Phase 2, a 2-year grant of $500,000 a year. It's funding, a lot of that is funding Marshall Advanced Concept Office. A lot of that's funding by graduate students, and South Dakota State University has a faculty member and a graduate student there that's on this project. All of them are listed on the web page. So thank you.
I'm going to miss this because I came in, but how does this enable you to detect dark matter?
Well, we would have to still have a dark matter detector.
How do you detect them?
Detect dark matter, you have an active volume, although that can be sensitive to some energy being deposited into the center. And you have an array of shells of photo rays around it to make sure absolutely nothing came in.
What arrays?
Photo arrays.
Like
silicon detectors are photo arrays.
To eliminate the background.
To remove the background. But a lot of the backgrounds is gamma rays. And the gamma rays can clearly go in and not produce any track going in. But if a gamma ray converts in the dark matter detector, it usually produces electron-positron pair going out. And then you can see it. And so the question is, how sensitive can we do it? Can we build enough layers to reject all the backgrounds?
And I thought most of the models for dark matter doesn't interact.
Right, that's
so
the
how
problem.
do you detect something that doesn't
Well,
interact?
that's an interesting thing that I've actually grumbled at NSF about for a long time. NSF is trying and spending a fortune to search for dark matter that they have no evidence that it interacts anything else except for gravitational.
Yeah, so how are they searching?
Weekly
They're searching with the hope that
It's a win.
Well, how are they searching?
Yeah.
They have to have something.
they're assuming it's going to be able to interact weakly and deposit some energy in some mysterious detector. And you saw all those mysterious detectors of all the different types in that one paragraph, on that one slide.
And they haven't seen anything.
No, they haven't seen anything.
Yeah.
So it's all, I mean, I agree with you. It's not clear you can detect dark matter except for gravitationally, but, you know, even NSF is spending a fortune on it.
Well, again, on this, with the same line here, if there must be some theory behind it, because you say that it's thought that dark matter accumulates in the core of the sun. How's it going to accumulate in the core of the sun if it doesn't interact with it?
Well,
it just goes straight through it, just like neutrinos, right?
No,
It interacts
it
gravitationally.
interacts gravitationally.
Yeah, but it doesn't. It interacts gravitationally. It's just going to oscillate.
It could oscillate.
It's going to oscillate in and out around the core.
It might
right?
clump
It's not gonna-
somehow.
Yeah. How would it clump? That's what I don't understand.
No, there are pictures of it clumping in the universe. There's dark matter maps that they say that they infer from gravitation.
Well,
And it isn't
they're
uniform.
alleged
And
to
it's not
be dark.
uniform, no, but they're
alleged to be dark
blobs.
matter.
They're alleged to be dark
Yeah,
matter.
but
I mean, I agree with you. I've actually dragged NSF over the coals on this in reviews of it, being on review panels of NSF. But then I'm now proposing something that is magically, mystically saying, well, we'll try to search for dark matter. But everyone else is saying that too, so I don't feel that guilty. Just a little guilty.
But I wonder, again, I wonder, how do they make these dark matter maps?
Oh, those dark matter maps are being, I was looking at the Brownian motion of stars and how they're moving with, and the influence that the non-visible light is making on the visible light
Well,
motion.
it's basically gravitation.
It's gravitation. So those are being made that way.
Convince me that neutrinos are not Marjorana.
Oh, I can. They could be.
They could be.
Neutrinos might be its own antiparticle. I'm on the NOVA experiment at Fermilab and on the DOME experiment.
Okay.
And we are about, on the NOVA data, about to make a statement of that.
Which way? Just like girls. What can you say?
I probably shouldn't say.
Okay.
It's an internal review of PRL that we're about to release,
Okay.
maybe in about 3 months.
But Jack and I argue about that case.
I mean, yeah, can the neutrino be its own antiparticle is an interesting.
Just to
I
make it
dedicated
more
a whole
difficult
chapter to
for
that
us
in my
all.
book. Yeah, it just needs data.
Right. Everything needs data. That's why we need people like you.
Well, there's lots of good things going on, just not this. But there's lots of interesting things in astronomy, astrophysics, solid state.
So it sounds like you've got a bunch of different ideas of how a neutrino detector in space could give us information. Are you thinking it's the same neutrino detector going to multiple places, or are you thinking of sending multiples?
These are different ideas.
Right.
And these are all just futuristic missions that the most advanced one conceptually is the one heading to the sun.
It would be the
Because
one
it's
going
being
towards
cost
the sun.
estimated by Advanced Concept Office at Marshall. The dark matter one, I get a little bit of money for it here and there, no more than like $60K per year. The gravitational focus of neutrinos, that we're just putting in grants for that because we just came up with this in June. We presented it at AAS in St. Louis, sort of almost a month after we conceived of the idea. And it just happened only because the man who heads the NASA project to gravitationally image an exoplanet was talking at the same thing I was talking at a NASA conference. And at the coffee break, we got together, and with a few internet searches, we found that some Russian theorist in the 70s already calculated the neutrino gravitational focus of the sun based on various mass options. And the project, the idea was born as a third thing we could do. Now, just as a side note, I'm not ready to put my career behind that one yet. But I had a senior thesis student work with me on calculating all of the neutrinos being emitted by the galactic core, the 10 to the 13th collecting power of neutrinos by our sun, and at the focus, the intensity should be 880 times the neutrino flux from our sun that we see here at Earth.
That's impressive.
Yeah, but I'm not ready to put my name behind that yet. That was just done with a senior thesis student. But that's interesting. 880. It's almost like 1,000.
Almost 1,000, yeah.
Almost 1,000. But again, that's very tentative. It's based on it wasn't a master's thesis, it was just a senior thesis, 1 semester student. She worked with me, and we hacked this out, and we think we got it right. But we need to double check.
So what does that number translate into detections per day, roughly?
Well, it depends on the size of the detector. If it's the planet Uranus or Neptune, it translates into tens of thousands of neutrinos interacting per day, and you'll see a blob of light on the dark side of Uranus or Neptune. It's not going to be in the focus point, it will be out of focus at the wrong distance. You'll see, and as the planet rotates, that blob of light stays put because it's from the gravitational focus. If the blob of light rotates with the planet, then it's something atmospheric.
So you could potentially do photometry.
Yeah, potentially. Again, that's a project. We're asking for funding from NASA for this for a graduate student, and to fund a fraction of a person at JPL Slava, who's joined this project with me.
What I mean by photometry is time series analysis.
Yeah.
Yeah.
Potentially.
Yeah.
Over years, of course.
Yeah.
As it moves through the center. As that single pixel camera called the planet moves across the face of the, as the galactic core moves across the gravitational focus, there's a single pixel. You get a line image.
Yeah.
So that's one thing that's interesting is you get a line image. You don't get a square image, nor do you get a cube, because these again would be separate experiments, one behind using the very
Well, you
large
get two
detector.
lines at least, Neptune and Uranus.
Well, that's if you can get one behind the
They're 30 years apart.
33.
Yeah.
That's only. It's not too long to get up there. Though.
Well, there is a project being designed that would launch in 2030 to Uranus. There is a JPL mission that's on the books.
Something for your grandchildren.
So it's very far in the future.
Another orbit.
Well, if there are no other questions, let's thank our speaker again. We'll go to the speaker out of the month, so if anybody wants to join us, you're welcome.
And sorry about the mess up with the slides.
It works.
It worked.
Well, somebody just had to push the right button.